Good morning. I'm Dr. Niti Maheshwari, Assistant Professor, Applied Science and Humanities Department, Ajay Kumar Garg Engineering College, Ghaziabad. Today, I'll be discussing about another spectroscopy which is known as Raman Spectroscopy. The name Raman Spectroscopy was given because it was discovered in 1928 by Sir C.V. Raman. Now, this Raman spectroscopy, it does not deals with the absorption of electromagnetic radiation, but it deals with the scattering of light by the molecules. Earlier, we have studied UV visible and IR spectroscopy. They dealt with the absorption of radiation. What are the effects of light when this light gets absorbed by the molecules? But this spectroscopy, it deals with the scattering of light, that what will happen or what happens when the light gets scattered. It is not being absorbed, but it gets scattered by the molecules, and it is only a very small fraction of light which gets scattered. So, when a beam of monochromatic light was allowed to pass through some organic substances, the light scattered, it contained some additional frequencies over and above or that of incident frequency. That means, when a monochromatic light was allowed to pass through some organic substances, then the light which is getting scattered by these molecules, they consisted of frequency of the same. Some frequencies were same as that of the incident radiation, but there were some additional frequencies which were over and above that of the incident frequency, and these were known as the Raman effect. Now, when a substance which may be gaseous, liquid or even solid, it is irradiated with monochromatic light of a definite frequency, then a very small fraction of light is scattered, because maximum light gets absorbed by the molecules. Because the molecules in that normal room temperature, they are at lower state, lower energy state. So, lower state, vibrational state. So, they absorb light to get excited, and the electrons, they can make a transition from ground state to the excited state, or even the rotational and the vibrational energy states are going to get changed. So, only a very small fraction of light, it gets scattered. Then Raman spectroscopy, it can be defined as a spectroscopic technique which is based on inelastic scattering of monochromatic light. If the light which is getting scattered, it is not of the same frequency as that of the incident light, that is the inelastic scattering of monochromatic light. Usually it is from a laser source, generally helium neon laser source is taken in the visible, near IR and ultraviolet region. Now, coming to the quantum theory of Raman effect. Now, this treats radiation of frequency nu as consisting of a stream of particles which are called as photons having energy h nu, where h is the Planck constant, or you know that capital E is equal to h nu. When light interacts with matter, the photons which make up the light, they may be absorbed or scattered. Then this photon having energy h nu, this may be either absorbed by the molecule or it can be scattered, or may not interact with the material. It is possible that it may not interact with the material and it may pass straight through it. There is no interaction and it passes straight through it. So, coming then, when light is scattered by matter, almost all the scattering is an elastic process. Elastic process, which means that the frequency of the scattered light is equal to the frequency of the incident light. There is no change in the frequency. That is, there is no change in the energy, and it is called the Rayleigh scattering. When the energy of the incident photon is equal to the energy of the scattered photon, then we say that Rayleigh scattering is happening. So, in Rayleigh scattering, it is an elastic process, which means scattered frequency is equal to the incident frequency. So, here you can see that the scattered frequency is equal to the incident frequency. Now, scattering which is taking place, it can take place in two ways. It can be inelastic scattering or the elastic scattering can take place. Elastic scattering, as I have already discussed, there is going to be no change in the frequency of the incident as well as scattered frequency. Incident frequency will be equal to the scattered frequency, which is going to give rise to the Rayleigh scattering. But if inelastic collision is taking place between the, if inelastic scattering is taking place, then it is possible that the scattered photon has less energy than the incident photon, or the scattered photon has higher energy than the incident photon. What I mean to say, that when a photon is going to interact with the molecule, or after hitting the molecule it is going to get scattered, then it is possible that the photon gives its energy, some part of its energy to the molecule, and it is also possible that the photon, it may take energy from the molecule. So, generally the molecules, they are present in the lower energy state. When they are present in the lower energy state, then the molecules, they take energy from the photon, and the frequency of the photon reduces after getting scattered. So, that gives rise, it gives rise to the Stokes line, which are the lower frequency lines. And if the molecules, they are present in the higher vibrational states, higher vibrational or rotational states, and if the photon collides and it takes energy from the molecule, which happens in very less cases, then it gives rise to the higher frequency scattering, because the energy of the photon has now increased. Therefore, the scattered photon will have a higher frequency than the incident photon. So, this formation of Stokes and anti-Stokes line, it gives rise to the Raman scattering, because here the frequency is not equal to the frequency of the scattering is not equal to the frequency of the incident light. Now, coming explanation for observing Rayleigh line and Raman lines. Why these lines are observed? Elastic and inelastic collisions between the radiations and interacting molecules result in the formation of Rayleigh and Raman lines. In terms of excitation of electrons, if the frequency of incident is equal to frequency of scattering, it is the Rayleigh line. If the frequency of incident light is greater than the frequency of scattered light, it is the Stokes line, and if it is less than that of the scattering, incident is less than that of the scattering, it gives rise to the anti-Stokes lines. Here in diagram I am showing how these are the virtual energy state, this is the ground level, these are the different vibrational energy states, this is the IR absorption is taking place. Now this first I am showing the Rayleigh scattering. In this Rayleigh scattering you can see that the difference in the incident frequency and scattered frequency, there is no difference between the two. Same frequency lines are getting scattered from the molecule. This gives rise to Rayleigh scattering. Maximum Rayleigh scattering is going to take place. Second, this is in terms of the molecule. Second is the Stokes-Raman scattering. In the Stokes-Raman scattering, as you can see, the frequency of the incident is greater than the frequency of the scattering. That means the photon has given its energy to the molecule, and now the molecule is going to return to a higher vibrational state. It is not going to get back, and the photon does not reach its original state and falls before its original state. So it gives rise to the Stokes-Raman scattering. And in the second case, the anti-Stokes lines, the molecules, they are present in the higher energy states, but when the photon takes energy from the molecule does not return back to its original state, it comes to a lower state or the ground level. Then it gives rise to the anti-Stokes line. But this process is very less. If we see the intensity, then the maximum intensity is of the Rayleigh scattering, then Stokes line, and then anti-Stokes line. Anti-Stokes lines are going to be very weak. Stokes-Raman scattering. Now, it is the process in which an electron, it is excited from the ground level and it falls to a vibrational level. As I was saying, you can see here, the electron is excited from the ground level, but it comes back to a vibrational level. That means that this has taken energy this has taken energy from the photon and it is not moving to its original ground state, but since it is taking energy from the photon, so it is elevating its energy. The molecule does absorb radiation with lower frequency than the incident light. Such Raman scattered lines which are observed in the small frequency side are called Stokes line, because the frequency has decreased. Therefore, the small frequency side scattered lines, they are known as Stokes line, because the frequency of the scattered line is less than that of the incident light. Anti-Stokes Raman scattering. Now, in this case, it is the process in which an electron is excited from the ground level. It is excited from the vibrational level and it reaches the ground level. Now, as I was showing in this diagram, the molecule, they are in higher energy state. They are in higher energy state, they get excited and then they fall to a lower energy state. That means the molecule have lost energy. They have given energy to the photon which strike this molecule. So, the molecule or the electron, it falls back to a ground level. When the excited molecule, it returns to the ground state, it emits radiation which are of higher frequency than that of the incident light. So, because it emits radiation which are of higher frequency than that of the incident light. Such Raman scattered lines which are observed in the higher frequency side, they are called called anti-Stokes line. And here the frequency of scattering is greater than that of the frequency of incident radiations. Again, I am showing the inelastic scattering. Now, how the energy exchange between the photon and molecule leads to the inelastic scattering of light. This is the incident frequency of incident radiation. If same frequency, that means there is no energy exchange between the photon and the molecule, then the frequency of scattered light is same as that of the incident. If the molecules, they take energy from the photon, then the molecule do not return to their ground level, their energy gets elevated, but photon, it loses energy. Therefore, the photon moves to the ground level, therefore the frequency reduces. And if the photon takes energy from the molecule, a part of the energy from the molecule, then the energy of the molecule decreases, but the energy of the photon increases, and if the energy of the photon increases, therefore frequency will also increase. As a result, anti-Stokes line, they are shown, they are produced at the higher frequency side, whereas the Stokes line, they are formed at the lower frequency side. Here again, a diagram between intensity and frequency. This is the Rayleigh scattering. Towards higher frequency side, anti-Stokes, lower frequency side, Stokes line. Now, if we see the intensity of Stokes and anti-Stokes line, then the intensity of Stokes line is more in comparison to the anti-Stokes line at room temperature, because the molecules, they are generally present in the lower state, lower vibrational rotational state. But when we increase the temperature, then there are chances that the energy of the molecules also increases, then the intensity of anti-Stokes line also increases. So, if we see the temperature dependence, then at lower temperature, Stokes lines, they are intense, whereas anti-Stokes lines are very less intense. But on increasing the temperature, the intensity of anti-Stokes line increases. Now, this Raman scattering, it is an extremely weak process, and only 1 in 10 to the power 6 or up to 10 to the power 8 photons, they get scattered. This technique, it is highly sensitive. Rayleigh scattering, it is the dominant process. As I have already said, that the maximum scattering will be Rayleigh scattering. At room temperature, the intensity of Stokes Raman scattering is more than the anti-Stokes Raman scattering, because at room temperature, most of the electron exist at the ground level. So, energy of molecule is less, so they are not in a condition to give their energy to the photon. So, the resulting Raman spectrum, here the production of Stokes line, this was 0 frequency, 0 vibrational state, first vibrational state, and this is the higher energy states on absorption of energy, and when they lose, when they come back, this is their energy. Similarly, for anti-Stokes line I have shown, and the probability of emission is proportional to the observed intensity. So, intensity of Rayleigh scattering is much more than the Stokes line, which is again more than the anti-Stokes line. And intensity of Raman lines are generally 0.001% intense of the, or they are 1.001% have the intensity of the source. So, intensity of Stokes line is very less. So, here I am showing E is equal to h nu. So, after scattering, this is going to be the difference between, this is known as the Raman shift. Again, this is the energy before scattering, and here the energy gets added up. So, this is the Raman shift. Now, here you can see it is minus sign. So, Stokes line, they are seen on the left side, whereas anti-Stokes line, they are seen on the right side, higher frequency side. Now, coming to the conditions for Raman scattering. Now, this Raman spectroscopy, it is observed only when a molecule show periodic change in polarizability due to its vibrational or rotational oscillation. That means there should be periodic change in the polarizability of the molecule, and polarizability, it is nothing but it is the measure of how easily an electron cloud is distorted by an electric field. If the electron cloud gets distorted, then the molecule becomes polarized, and when the molecule becomes polarized, then it is said to induce dipole moment in the molecule. So, for any molecule to be Raman active, it should show the periodic change in the polarizability. If we can observe this, only then the molecule will be Raman active. Now, polarizability of molecules and Raman spectra. Now, the Raman effect, it arises on account of the polarization, that is the distortion of the electron cloud of the scattering molecules, that is caused by the electric vector of the electromagnetic radiation. Now, the induced dipole moment depends upon the strength of the electric field and the nature of the molecules. So, the dipole moment, it depends upon the polarizability and the electric field. How much electric field, or what is the strength of the electric field. So, when the molecule is polarized, that is its electron cloud distorts. If you are able to distort the electron cloud, then it is going, there is some dipole moment is going to get induced in the molecule, and then our molecule is going to be Raman active, or it is going to show the Raman lines, the Rayleigh lines, the Stokes line and the anti-Stokes lines. Now, in case of atoms of spherically symmetrical molecules, that is having spherical rotors such as CH4, SF6, same polarizability is induced whatever be the direction of the applied field. They are said to be isotropically polarizable, and then such molecules are said to be isotropic molecules. Now, these molecules CH4, SF6, they are isotropically polarizable. That means their polarizability is same in all the directions of the applied electric field. So, such molecules, they are not going to be Raman active, because there is no change in the polarizability, no charges are going to be developed. Therefore, there will be no induced dipole moment in the molecule. Whereas in case of all diatomic molecules, whether they may be homonuclear or heteronuclear, and non-spherical molecules, the polarizability depends upon the direction of the electric field which is being applied, and such molecules are therefore said to be anisotropically polarizable. And therefore, the polarizability of the molecule must be anisotropic. That means it must depend upon the orientation of the molecule. So, if the orientation of the molecule is going to change, the polarizability will change. As a result, change in polarizability will induce dipole moment in the molecule, and only then the molecule will show different lines, scattered lines in the Raman spectrum. Now, hence all diatomic molecules, linear molecules and non-spherical molecules, they give Raman spectra, and therefore they are rotationally Raman active. So, they are going to be Raman active molecules. For example, H2O2, and different examples are given. So, these all molecules are going to be Raman active, and on the other hand, the spherically symmetric molecules like CH4, SF6, P4, UF6, they do not give rise to rotational Raman spectrum. That means they are rotationally Raman inactive. These molecules are also rotationally microwave inactive. So, these molecules, they are not going to show or give any Raman spectra. Now, conditions for Raman spectroscopy. Vibrational modes are more polarizable and are more Raman active. In comparison to the rotational modes, vibrational modes, they are more polarizable, therefore they are more Raman active. For example, N2 molecule. Now, if you remember the IR spectroscopy, for a linear molecule, the degree of freedom, the vibrational modes were calculated as 3n minus 5. Suppose I am taking the molecule N2. Since the number of atoms are 2, so n is 2. So, 3 into 2 minus 5, 6 minus 5 will become 1. That means its one mode should be IR active. Now, since in homodiatomic molecules like N2, H2O2, there were no dipole moment was being produced. Therefore, they were IR inactive. They were IR inactive because they could not change, there was no change in the dipoles. But these molecules show change in the polarizability of the bond. As the bond gets longer, it is more easily deformed. Therefore, these molecules are Raman active. So, this mode of vibration of N2, which we are not getting in the IR spectroscopy, this we are going to get in the Raman spectrum. That means IR and Raman, for some molecules, they are related to each other. If one mode is going to be active, the other one will be inactive. So, that is generally for molecules having center of symmetry. So, here the N2 molecule, the symmetric stretching does not change the dipole. Here N, so here only one mode, that is symmetric stretching, it will not produce any change in the dipole moment. So, it is not going to show any absorption peak in the IR spectrum, but there is a change in the polarizability of the bond. So, it is when the light is not getting absorbed in the vibrational spectrum, it is getting scattered. As the bond gets longer, it is more easily deformed. Therefore, this N2 molecule becomes Raman active. Coming to similarly to CO2 asymmetric stretching. Now this asymmetric stretching of CO2, it causes change in dipole. Here I had taken this example in IR spectroscopy also. So this is the asymmetric stretching in the CO2 molecule. So the dipole moment at one end of the vibration is different from the dipole moment at the other end of the vibration. Therefore, this asymmetric stretching is going to be IR active. Polarizability change of one CO bond lengthening is cancelled by the shortening of the other. But here there is no net change in the polarizability of the molecule. Therefore, this asymmetric stretching, it becomes Raman inactive. Some modes may be both IR and Raman active, and others may be one or the other. Some modes of vibration can show both IR absorption also and Raman scattering also. But in other case, if it is going to be IR active, one mode of vibration will be IR active, then it is going to be Raman inactive and vice versa. Raman selection rules. Now, for rotational Raman spectroscopy, the selection rule that we are following, that the change in rotational energy level should be of plus minus 2. This is the rotational quantum number, J is the rotational quantum number, and this is the specific selection rule. In Raman, the rotational quantum number changes by 2 units rather than 1 because of molecular polarizability. Thus, the polarizability changes with the frequency, which is twice the rotational frequency of the molecule. So, the polarizability changes with the frequency, twice the rotational frequency of the molecule, and this rotational quantum number for Stokes line, it is plus 2, delta J is equal to plus minus 2. So, for Stokes line it is plus 2 and for anti-Stokes line it is minus 2. Vibrational Raman spectroscopy. Now, the polarizability of the molecule must change during a particular vibration, and the delta nu for Raman also follows plus minus 1, where nu is the vibrational quantum number, and for Stokes line delta nu is plus 1 and for anti-Stokes line delta nu is minus 1. Raman shift. If nu I represents the frequency of incident radiation, if this is the frequency of incident radiation and nu s is the frequency of scattered radiation, then the Raman shift delta nu is given by nu I minus nu s. Therefore, if we see for Stokes line, this value is going to be positive because frequency of incident is greater than the frequency of the scattering, and for anti-Stokes line this is negative because frequency of incident is less than the frequency of the scattered light. Now, in the molecules with center of symmetry, having center of symmetry, it is seen that vibrations that are Raman active, they are going to be IR inactive and vice versa, and this is called principle of mutual exclusion. For molecules which do not have center of symmetry, this rule is not applicable. They can have both Raman active as well as IR active, but the molecules having center of symmetry, those vibrations which are going to be Raman active, they are necessarily going to be IR inactive, and those which are going to show IR absorption will not give any Raman scattering line. and this is called the principle of mutual exclusion. Here I have taken the example of CO2 molecule. Now the vibrational mode in CO2 molecule, this is symmetrical stretching. In the symmetrical stretching, you can see there is no change in the dipole moment, because both side oxygen, they are stretching with the same frequency, so no dipole moment is getting changed. But there is change in the polarizability. If the polarizability changes, then this frequency becomes Raman active, but this frequency is IR inactive. But in the second case, where is it is unsymmetrical stretching, which is the anti-symmetrical stretching, here you can see there is stretching, then there is change in the dipole moment. The one end of the molecule, dipole moment at one end is different from the dipole moment at the other end. Therefore, there is a change in the dipole moment. But polarizability, there is no change because the dipole moment itself is getting changed. Therefore, this vibration, specifically this vibration, anti-symmetrical vibration stretching, it is going to be Raman inactive, but it will be IR active. Here I am showing diagrammatically the symmetric stretching vibration of CO2, the polarizability changes, and the Raman band is observed at 1340 centimeter inverse, and the dipole moment does not change, therefore no IR absorption band. This is the asymmetric stretching vibration of CO2. Here the polarizability does not change, therefore no Raman band near 2350 centimeter inverse, but since the dipole moment changes, therefore the IR absorption band is observed at 2349 centimeter inverse. Again, symmetric stretching is going to be Raman active, asymmetric stretching will be IR active but Raman inactive, and this bending, there were 4 modes which were active. So, these 2 bendings, they are going to be IR active because there is change, there is getting deformed, therefore there is change in the dipole moment, but there is no change in the polarizability, therefore they are going to be Raman inactive. Coming to the applications, now the Raman spectra, it provides a fingerprint by which the molecule can be identified. It is used to detect explosives for airport security. It is used to discriminate between healthy and unhealthy tissues. It is used to study the biological systems. And the Raman spectra, it helps to investigate the chemical composition of historical documents. Now, coming to the difference between Raman and IR, which are important. Now, this Raman, it is caused by the scattering of light, not by the absorption, but by the scattering, whereas the IR, it is caused by the absorption of light by the vibrating molecules. The vibration is Raman active if it is causing a change in polarizability, but the vibration is IR active if there is a change in dipole moment. Homonuclear diatomic molecules, they show Raman spectra because they are IR inactive, and the homonuclear diatomic molecule, they do not show IR spectra. We can study biological systems because water can be used as a solvent, but in the case of IR, water cannot be used due to the intense absorption. Water start getting absorbed. Then the sample preparation is not very elaborate. Sample can be in almost any state, but here the sample preparation is elaborate. Gaseous samples can rarely be used. The cost of instrumentation is very high in the Raman, and IR, it is comparatively inexpensive. In comparison to Raman, the cost of IR is less. Thank you.